All right, if you missed the kinetics lesson, we are going to review it now. So the learning target is I can explain factors that affect kinetics, reaction rates. I can explain collision theory with regards to chemical reactions with varying concentrations of solutions. So in the introduction, it says that kinetics is the study of the rate of reactions. So there's some reactions that are very slow, like things that are rusting. Imagine like a nail that's rusting over years and years. And then there are reactions that happen really quickly, like when we blew up the hydrogen balloon. So hydrogen in the presence of oxygen and a flame takes just fractions of a second with explosive force. Earlier in the year, we learned about the kinetic molecular theory of gas molecule behavior, and it is going to set the foundation for collision theory. So let's review. Gas particles are in constant, random motion. They move in straight lines. The speeds of the particles are not all the same. They have a lot of space to move around in. As temperature goes up, their average speed goes up. They move faster and therefore bounce harder off the walls. At lower temperatures, they move slower. And if they're in a flexible container like a balloon, you can imagine the volume will shrink because they're not hitting the walls as often or as forcefully. And so they would shrink down when cooled. So collision theory was developed from the kinetic theory of gases to account for things like concentration and temperature on reaction rate. It's based on three things. Number one, reactions occur when particles collide with one another. A collision only results in a reaction if a certain minimum energy is exceeded, and a collision will not result in a reaction unless the colliding particles are correctly oriented to one another. All right, let's talk about this in the context of some demos that we did in class. So in class, we had just like a piece of metal with some flour on it, and it kind of got scorched. And then when we put flour in a bottle and sprayed it over a flame, there was like a huge ball of fire. Why did that happen? Well, the fine flour particles have a higher surface area, and so the flame was able to burn all sides of each little piece of flour compared to when they were in bulk on just a piece of metal. So not as much surface area here. So increased surface area increases the rate of reaction. Then we did another one where we had cold vinegar versus hot vinegar in flasks with balloons over the top. And inside the balloons, there were 3 grams of baking soda. So they were kind of sitting here until we lifted up the balloon and let the baking soda in. So there was one that was hot and there was one that was cold. And after we put the baking soda in, the hot balloon blew up very quickly, and the cold balloon took a while to blow up, and eventually it did, but it took much, much longer. And the reason why is the hot vinegar, the particles are moving really, really fast. And so there's an increased number of collisions with the baking soda particles, which increases the reaction rate. And we did another experiment where we had a beaker of 1 molar hydrochloric acid, and we had 3 molar hydrochloric acid, so more concentrated. Put a little strip of magnesium in each. And in the one that was 3 molar, it was fully reacted in seconds. It was very, very quickly. Versus the one that was 1 molar, it was much slower. And the reason why is because there's more HCl molecules to react with the magnesium, there were more collisions, and therefore there was a faster reaction rate. And then last but not least, hydrogen peroxide will decompose into water and oxygen gas over time. If you add heat, if you add light, it happens very slowly. And then we did an experiment where we added a catalyst, potassium iodide, and the reaction happened very, very fast. And it's a little bit different here for a catalyst. If you've got an energy diagram, what a catalyst does is it lowers the activation energy. So it makes the reaction faster in a different way, in different mechanism. So it lowers the activation energy required to get the reaction going. And then these concepts are reviewed again down here. So if you want to take some time to kind of read through, it goes through those more like a textbook. And then just to kind of end with some practice problems, what factors can affect the rate of a chemical reaction? The presence of a catalyst, the temperature, the concentration, the surface area of the reactants. So how would rate of reaction be affected and why if you lowered the concentration? Well, then you would lower the reaction rate because there would be less opportunity for collisions between the reactants because there's less solute per liter. If you increase the temperature of the reaction, you're going to increase the reaction rate because there's more collisions because the molecules are moving faster. And so they're just going to hit each other more often. They've got more kinetic energy. The presence of a catalyst is also going to speed up the reaction rate. And the reason why is because it lowers the activation energy, making it easier for the reaction to proceed. Does every collision between reacting particles lead to products? No. They have to have the minimum energy required, at least. Okay, in other words, enough energy to break the bonds of the reactants, the activation energy, and they also have to be oriented in 3D properly when they collide. The addition of a catalyst to this reaction would cause a change in which indicated energy difference. It would be 1 because a catalyst would lower that activation energy. Energy 3 represents the heat of reaction. It's the energy difference between the reactants and the products. And how are 1 and 2 related? 1 is the energy in to break bonds, and 2 is the energy released as new bonds form. So that is kinetics in a nutshell.